Okay, so for those of you who might have just stepped in and missed introductions during the panel or missed Sam's talk this morning, I'm Eliza Edison, VP Operations here at Applied Computing, and this is Sam Tukra, our Chief AI Officer, and we are very excited to introduce you to Orbital. Orbital is our core technology through which users can access and harness our powerful, precise, and proprietary AI models. These language, physics, chemistry, and time series models are harnessed and cultivated for our users by training them on all available data. We were talking about this previously on the panel, but that means everything from greasy handwritten notes to CSVs, thereby taking all of the world's horsepower on a topic and turning it on to their specific needs. I'm going to take a moment and explain what some of those needs are in a refinery to make this very complex and technical world relatable and clear for those of you who might not be familiar with it, a little bit like Orbital does. At a refinery, our users' needs are concentrated in 5 key activities: distillation, cracking, hydrotreating, reforming, and blending, or for those of you who don't own your own pair of steel-toed shoes, that means you have to separate again, clean it, upgrade it, and then mix it just right. For each of these and all the associated steps and components and machinery, you need the right answer to thousands of decisions a day, 24/7, 365, and you need them as quickly as possible. Currently, to get those answers, our users have a wide variety of tools, such as this one, where I would manually create a process flow diagram by dragging units from this right-hand menu onto the screen. And then when I wanted to run a simulation, I would click a particular unit and then type in the range of figures I wanted it to simulate. I take the output of that tool and I put it in Excel and fuddle around with it in my model. And then I go back to the tool and iterate back and forth to find something I want to submit for approval. Or if I was a reliability engineer, I would use a different tool entirely. This one is designed to make physics-based predictions of when failures or anomalies might occur. Once it finds one that might, it'll surface it to a team, which is then taken away to a team of experts to investigate possible root causes and possible remedial action, hopefully in time. These 2 tools are typical at each site, but are only 2 of dozens of tools used by these teams. And while all of them rely on common data, they all use different specialized systems in a largely siloed manner, and none of them uses all available data. To put a very fine point on it, they're using only 8%. And this lack of shared context and lack of complete access to data leads to a number of inefficiencies, as you can only imagine. Often we find that at many sites, only 10% of reliability alerts are acted upon, and over half of optimization improvement recommendations are actually implemented. 90% of reliability alerts are ignored, and they are functionally doing a coin toss as to whether they should implement an improvement recommendation. And it's no wonder, because they only have access to 8% of their data. That's like doing analysis with one hand tied behind your back and a blindfold on. We think there's a better way for these thousands of people to be able to access these myriad decisions they need to answer on a daily basis. And it's with Orbital. And welcome to Orbital, which is currently live. So understandably, our users aren't particularly thrilled about us sharing their data publicly. So this particular instance of Orbital is trained and running on Imperial's ABB carbon capture plant in South Kensington. That means 2 things. 1, you will see real data live from a carbon capture plant a mere 10 tube stops away. And 2, you guys get to see some features we're developing in beta before even some of our customers get them. Last bit of housekeeping, I'm under strict instruction from the team that I'm only allowed to show you a very small subset of the features that we've developed that is purely for the purposes of getting you home in time for dinner. All that said, Orbital brings together the data access requirements for a site, and as a result, users will interact with it differently because, as we were talking about on the panel, we need to meet users where they are with the workflows they need. But for the purposes of this demo, I've set up a generic user that has access to a lot of the functionality of the tool. Unimaginatively, I have named this tool in homage to its creator, Sam. So a user might click on the process flow diagram, which is, this isn't, sorry. Can I have the demo back, please? No, yeah, right. That, I would have been much more clever had I made a recording.
I think you're trying to show the
Yeah, I am. This is the trouble with someone.
Multi-finger moves the window, 2 fingers moves the mouse.
Two, okay. We should have calibrated our touchpad instructions. Okay. Thank you all for indulging me in that. So a user might consult the process flow diagram, which they would move with only 2 and not 3 fingers, which has all of the units in the carbon capture plant labeled with all of their sensors actively being updated. Or they might consult the live feed, which is customizable with natural language queries for each and every user. So they can ask the questions they need to and get the information most critical to their workflows on a regular basis. Or perhaps for some of the frontline users who are not as comfortable with written language, they might stay entirely on the home screen, where Orbital can take spoken inputs and provide audio outputs in multiple languages to guide their work. That said, today we're going to step into the shoes of one of those APC engineers we've heard a lot about today, responsible for thousands and thousands of pieces of machinery. And they might start their morning with Orbital by asking a very simple question. Give me a summary of the plant in its current state. Very quickly, we'll see how Orbital understands data. And what I want to be very clear about is that Orbital is not asking one question with predefined fields that it's populating into a template script. In the time it's taking me to explain this, Orbital has consulted each and every sensor in this plant. It has gotten the current readings. It has then consulted all historical data to understand historical and all past performance for the plant. And it has then considered that in parallel with all of the knowledge available on the internet of physics and chemistry. And then lastly, before it starts telling me about it, it considers me as a user. What do I need to know? What is my role? What are my responsibilities? What is my level of technical background such that what this question actually means to me? And it has done that in less time than it has taken me to explain it. But of course, we don't just want status. We want to be able to do something with it. So let's see some cooler things that Orbital can do. What if I asked, what is the most impactful you can tell it's live because of the typos, improvement I can make to my plant? And maybe because I want to do something with it, I'll have it format the response as a report. So I want to ask you to cast your minds back to the slides I was showing just a moment ago, where they would go back and forth between tools and Excel models to try and generate these simulations and come together with a report that had a 46% chance of approval. By harnessing all the available data in a plant, Orbital brings superintelligence to these users. So instead of iterative back and forth and at functionally educated guesses, it's bringing the right answer to the user exactly when it needs it. What I particularly like is that Orbital will settle the overview here, which kind of works how my brain does. I start at 30,000 feet, and then I can zoom in or really understand. I'm trying to scroll, Sam. I'm trying to, okay. I got it. I'm so sorry. I swear I'm not an idiot. I just have a different trackpad set up. Where Orbital explains its math and it shows it's working. Because as we've said so many times today, trust is paramount in these industries. And so I can read through it and make sure I understand it. And if I didn't trust something or didn't understand something or didn't think it was right, all I would have to do is highlight it, put it back into Orbital, and ask some more questions. But let's say I trust this one, because I happen to, and I want to do something about it. So I'll say, Orbital, can you send this report to my manager for approval? And it's off. to my manager. So I suppose wherever Cal is in the audience, please check your inbox for approval. And so here's the thing. Orbital can go beyond day-to-day decision support. It can also help us ask those long-term questions often asked in these heavy industry sites, like what if? To talk you through that functionality, here's Sam. We're going.
Yeah, that's still clear to everyone, right? It was just too big for me. Okay. So one of the coolest things that I found about building this with the team here was that every response style, the tone, the output was by design. It wasn't just what the model was creating. We actually consulted and collected tons of feedback from APC engineers and operators in terms of the kind of language they expect to see, and use that to train the model and directly embed it as part of the response structure. So that output and every answer Orbital give is tuned to the user's actual needs and understanding. And what you just saw was Orbital interpret, understand, and predict, all within just 15 seconds of prompting per prompt. But one of the key things they do in the industry, and by they I mean our control engineers in the room, would be to plan what would happen if you were to change something. And this is typically known as what if, or what if scenario planning. As in, what if I change this dial? What would happen to my end product? What if I change the temperature of this particular feed? In which case, what would happen to the actual entire process? This what if is the ability for them to simulate changes without having to directly implement them on site, which isn't possible to do given the expense and the consequences that go with the experimentation. Now, right now, what if is done by stripping that 8% data, selecting certain variables, and creating a very large spreadsheet with a correlation matrix where you basically color code what has the relationship of the largest change. I looked at it. I didn't understand it, so I didn't like it. They didn't like it either, so we decided let's bring some change into it with AI. So in the case of what if I wanted to change, well, if I wanted to simulate what would happen, should I change certain variables? All I'd have to do is click on the what if. Oh wow, I can sound louder. So I can click on the what if and simply define the targets I would change. So in this case, let's play with the temperature setting. We'll also play with the density of the solvent going through the plant, because the main aim of carbon capture is to maximize carbon removal through the solvent that's going through the actual equipment that makes the maximum absorption. Let's also change flow, which is currently shut. So if I was to do 12, let's increase that to 2 and increase this to 2 as well. Now, remember, typically, weeks of Excel, correlation, only a small portion of data. Instead, when I hit run, it will appear as magic, but it is not. It will be processing all 100% of the data in the background, predicting exactly how all of the other sensor variables will change based on the grounding and understanding of physics, and then give me an explanation of it so that I can then understand in plain English, in a language that every operator and engineer would understand, what the impact of that is. Right? So we see how other top 10 sensors get affected by exactly how much value change, and then an explanation that tells me exactly the change to a high significant digit, including the analysis of it. So notice the language here isn't wishy-washy, like likely, maybe, this will happen. It is precise because it's guided by the computation of the time series as well as the grounding of the physics to understand what's actually happening. Now, the thing is that in my case, this didn't exactly hit the mark for how do I maximize my carbon capture. But I did get an understanding of what will happen if I were to change certain sensors and the impact of that on that current operation. So instead of me spending more time to figure out what configuration would work, which is a bit arduous, let's just ask Orbital. I really hope I am typing. Yeah. Okay. CO2 removal. Okay, let's do that. And what will happen, I hope. Yeah, okay. Yeah, so notice it's now going to search the exact sensors that relate to the very measurement I need to do in order to understand carbon capture and maximize it, which is basically targeting the solvent feed and how it's going to flow and process through the entire operation. But then now it's actually going to do the mathematical calculation of what will change in the background. So whilst it's loading, it's actually doing additional computation. Now, if you scale that to something like a refinery, that's doing almost 200 million computations for that 1 minute interval. And it's going to process that data, in this particular plant's case, about 250 sensor variables. And then it will interpret and explain to me exactly what the change is. And because we don't want to bludgeon the operator with too much info, it automatically summarizes the overview to be very precise in terms of what needs to be changed in order to achieve that very goal that I simply just gave it as a natural language query.
Sam, sorry to hop in. I'm just curious. That first input that just came in there as variables, were they real time?
Yeah. It's still taking it from the process historian of the carbon capture lab.
So within recent minutes.
Yeah, so there will be a default one that we have taken for the demo, but there are additional variables that you can change if I was to elongate the length of time if I wanted to process more. In the interest of time and to reduce my computation time, that loading bar would be a hell of a lot longer if I was to process entire 4 years, but let's not do that.
Sorry, resource-wise, what's this running on at the moment?
This is running on the very same edge box that we would actually deploy for our production. The only difference is this is right now running in our cloud. But the configuration is the exact same that would be actually shipped to the actual on-site for plugging in.
So if you decided to expand the refinery and have more sensors, etc., another box?
No. We have designed the box to cater for one entire unit. If you expand to multiple units, then yes. But yeah, so now I have understood how I want to maximize my carbon capture, but I want to kind of implement this in the front line. I don't just want to get that insight for myself. So let's actually generate an implementation plan so that the operators can utilize the information that you usually get from what is known as standard operating procedures so that they can just go out there and put this in action. So can you generate a plan? Maybe I should add please like they do in many of the demos. Plan to implement this new condition. So automatically, it's going to now consolidate everything that was just found from the time series model and convert them into exact current and target range we should achieve and the justification of it in really clear summaries, because remember, this will go to the front line. This will not remain within Orbital. So we need to reduce that burden of understanding to make it as fast as possible, because the people that are actually the operators aren't the ones with fancy degrees in engineering. So this converts it directly to those action points, and it retains the reasoning for the lead operator to make a decision on in order to understand how to take it forward. So instead of spending weeks on Excel that you would when you're doing what-if planning and just understanding how to run your operations, Orbital takes the precision of that time series data as well as the physics that we've trained it for grounding to the actual process, gives me not just the answer to what if, but also the why. Right? But yeah, the cool thing that we're also going to do now, which I'm going to hand over to Eliza, is what happens and what Orbital does when something goes wrong. Hang on, let me move my mouse before I ruin the demo. There we go.
Thank you. I can ruin it all on my own. So shortly, I'm going to force Orbital to push an alert about a critical anomaly. I want to clarify and make quite explicit that this particular demonstration is artificial. That means that all is well in SW8. There is no need to rush and rescue all the priceless artifacts at the VNA, but that said. So in this particular alert, we see that there's a critical anomaly with some flooding in the absorber. I want you to cast your minds back one more time to the slides I was showing you at the beginning of our talk about how 90% of these are ignored. They're ignored because the alerts come with no context, or they're inaccurate, or they are useless, or they don't tell them anything they can do about it. It's just a flashing light in a corner. What Orbital provides is the right alert at the right moment to the user who can do something about it. And it doesn't just tell you that it's happening, it tells you why. So I don't think there are any carbon capture plant operators in the room. You will have to trust me that if you were one and you got this alert, it would make you very nervous. And you might have the very human response of simply typing, "What do I do?" And very quickly, Orbital will provide an answer. Because again, a dashboard can tell you that something is off, but it can't tell you why it is or what to do about it. Orbital considers all context and exactly who I am as a user to think about the most impactful thing I could do to stave off disaster. And it does it so quickly, in Sam's words, it seems like magic, but in the words of my high school physics teacher, no, that's science. Orbital is a symphony of intelligence for the industrial frontline and unlocks AI for heavy industry. It unleashes the power of, it brings to bear Britain's third ever foundational model on the industrial frontline and unleashes the power of sustainable abundance. To help you understand how we made it, to use his trackpad accurately, and to tell you why our users love Orbital so much, here's Sam one last time.
Okay, so I think this is where we go into the science of things. But before we do so, I really hope you guys are okay if I just have a glass of water. But yeah, this is going to be the fun part. Not that other parts weren't fun. Other parts were also fun.
Sam, before you go on to that next part, does it also do things like help you predict and schedule downtime as well? And recommend that?
Do I have to answer about the feature that we have?
Oh, okay.
The answer is yes.
Yeah.
Yes. So right now what you'll see is its biggest case is because it's been grounded by the understanding of entire plant, it can answer any query you give it about the plant. What we're now working towards is the fact that with some of the pilots that we're running, there is a guided messaging way of how they would interact with the information that they get from Orbital. So it's really the case of customizing those different needs. But the core information comes directly from the model that's been embedded there. Just put it there for a second. Okay. How many of you want to know how we built this? Oh, wow. Okay, nice. I'm so glad you guys lifted your hands. Okay, so we talked about the fact that trust has to be foundational, right? So one of the biggest challenges I had, and I see my principal researcher right there staring at me so that I do him justice, is understanding how do we put this in an algorithm and write it out in code, in math. And what we realized is that our algorithm had to be something more multifaceted, which catered for the fact that it has to understand information that is coming in real time. So 1 minute interval, maybe even sub-second, depending upon where you deploy it. It has to be real time, and that was non-negotiable. It also had to ensure that every real-time inference followed by a feedback to its own self so that it can improve, but also understand what was the previous action that it took in order to inform the next. It also had to make sure that there was no hallucination at all, because unlike the internet world, we don't have the luxury to give wrong information. Not in this case. It had to adapt to all of the live changes that are happening in the refinery, and luckily that's also reflected in the data itself. But it's a case of reasoning with that information and inferring that that change is the driving factor, whilst making sure that the physics of the entirety of the unit and the operation at hand is understood, grounded to every time series prediction that you do, because simply predicting the next number or forecasting the value is not enough. We need to be able to explain why that number and what that means for the plant to make it valuable. Finally, it had to achieve the level of precision required for every task that it's deployed on. So when you actually put a query through Orbital, it's not just going through one model. It's going through multiple models that interact with one another to achieve all of this in unison in less than 15 seconds. So something like this would happen essentially. Query goes in, and what happens is the first model it goes through is known as the router model, whose job is to dissect the query and send it to the relevant model in order to infer the right information, whether that's time series and physics or whether that's retrieval, whose sole purpose is to extract all of the information from the unstructured documentation of any plant to inform the answer so that everything remains grounded to that exact plant. And then the verifier model, whose purpose is to make sure that there is no hallucination, it's grounded to reality as well as factual accuracy. And all of these models are inferred in sequence and finally converge to an answer only when the verifier says a green light does the answer pop out on the actual application. And every time a query goes through, you go through that many computations every 15 seconds. So let's actually dive into these individual models itself, focusing first on the time series and physics because they're very conjoint in terms of how we designed them. This was actually the most exciting and the difficult part of it, actually, because it's the first core engine to get the numerical figures right. And at the end of the day, precision comes from these models. Well, these two models, essentially. So in today's deep learning, let's say I'm a data scientist. I've been sent to a refinery, and I'm the happiest man. I actually was when I was sent to a refinery. It was freaking awesome. They also give you chai in India when you're there, so fantastic. I was given more data than I could ever have imagined. If we consider how Llama was trained, which is about 3.4 terabytes of data, if we were to collate all of the data from refinery, from all of the units over multiple years, we're talking about almost 90 terabytes in comparison. So all of that data right now, if I have a deep learning model, which is the de facto AI model right now, no matter where you go, you must have heard the term transformers, etc. That's the hot stuff. Ultimately, still a black box. So all that data goes into a black box to predict something. And deep learning is powerful. It can detect patterns no human ever could. But there's a catch. It doesn't know why. It will just predict the right number based on the trend. But the problem occurs when something goes wrong. Because when things go wrong, and as they always do, from that very deep learning model that's been deployed, you just get silence. No cause, no reasoning. Just the numerical figure of what will happen next. And in heavy industry, that's not just a limitation, that's actually dangerous. So if we look at what models are deployed today in the front line, and we were to plot them in terms of how well they perform, fidelity and trust, these are the three typical groups that come into play. Linear methods, traditional machine learning algorithms, stuff like random forests, support vector machines. Support vector machines were really awesome, by the way. That's how I started AI. And I could see the person who actually taught me AI right in front of me smiling. And then, of course, you also have deep neural nets. How many of, actually, show of hands, what do you think is, which of these models actually runs in refinery today? Show of hands for linear methods. Okay, fair amount. Show me the number of hands for traditional machine learning algorithms that are running today. Okay. And deep neural nets? None. Okay, fair. Wow, yes, you're right. Majority of systems today, linear methods. because they're the most explainable. That is what the industry runs on right now. And the kind of model that we needed to create was considered the factor of not only fidelity, but also trust. So we needed to be way in that upper corner with our time series of physics model in order to drive true transformational value. Now, the beauty was what seems to be always the difficulty in AI. So you must have heard people say, unstructured data is rough. The real world data is messy. It's not labeled. It's missing factors. It's not really well organized. What is choppy waters for AI in the internet world actually became an advantage to create AI for this world. Because the very first rule we defined for creating our time series model is that every prediction must obey the first principles of physics. Every prediction. So typically when you get a neural net, which is a bunch of neurons that are just interconnected, just like the rewiring of a brain, they would essentially just take the data going in, get some probability values in between each of those nodes, and then generate a response. But in order to make this predictable, but also actionable, well, to be able to explain where that reasoning comes from, when we zoom into these nodes, what we designed them with is to encode the actual physics principles that is informed by the language model. So when a query goes in and we give it a question about a particular process, the language model concocts the relevant physics equation that is defined for that process as a whole. And the foundation models, every single node essentially encodes each a physical equation for that particular process defined by the language model. And it would take all of that real-time data and estimate the coefficients of that physics model. And this really blew our minds away because we basically just said, instead of doing probabilities, let's estimate the coefficients that define the physics model. And by designing the neural net in this way, so you must have heard of physics-informed neural nets, etc., similar structure. The beauty is, given that the coefficients are informed by the real-time data, it became a very dynamic model on its own because the coefficients changed with the real-time information. So the physics actually became an evolving structure itself. Whilst the model's job was to understand the distribution of actions taking place, the physics model's job within this was to estimate the right physics equation for the right time for the right data point. And all of this was happening live. So it suddenly did not become a black box anymore. So what happens is when we ask it a particular query to explain, essentially, we would take one of these relevant nodes, that's what the language model's job is, and would literally extract the physical equation, ask what are the new coefficients, and inform itself based on the first principles of the physics equation and the forecasting of the time series, how to explain the actual output. Because physics was ingrained within the time series model itself, every node's prediction became explainable. No matter where I extracted, depending upon the weight and what its contribution was to the particular query and task, I could essentially extract and target that exact weight point and extract the answer, and therefore make every single prediction and every single node that led to it with the highest probability explainable. And the coolest thing is, because we were able to do that, we actually ended up having a foundation model grounded in physics with the power of deep learning right in that corner. But then we ran into a very tough challenge. How do we put this in front of a user? And when I spoke to a control room engineer, the first question that they asked me is, are you going to give me another dashboard? I said, yeah. And they weren't happy with that initially. And what we realized is dashboards aren't really informative. Because if 1, 2, 3, 4 dashboards didn't solve this problem, why would the 5th? And the thing we realized with the dashboard is even if you give these figures that we've now so carefully forecasted as a graph, the interpretation is left to the user, which will differ from person to person. So we needed a new way to do this. And that's where the language model came into play. is we made that our main user interface so that the messages are clear and directly extracted from the data itself. So with that in mind, we're going to dive into the two other models. And this will answer your question as well, sir, what you asked earlier with regards to how do we verify the accuracy part? Because essentially, the first language model, retrieval model's sole purpose is to essentially understand the entirety of the plant and bake it into its memory through user manuals, logs, documents, etc. And the cool thing is that when we actually started to train it, we actually did it with a condition that it should refuse to guess. So there's this thing called the temperature parameter in language model, and we said, no, we're not going to use any of that. You cannot guess. If the document isn't there and a passage cannot be found in order to define a particular answer and reason, it will just ask, I don't have that information. It won't invent. If the procedure doesn't cover it, retrieval must ask. It cannot invent. That was very fundamental to the learning algorithm that we created, because control room credibility was non-negotiable for us. And the cool thing that we found is when we trained the retrieval model on a bunch of different text, right? So here's an example of it. When you have text, typical models are trained by basically fill in the blanks. You give it a bunch of text, you obscure the other pieces of text, and you train the model to essentially regenerate that text. And you do that enough times, that's how language models learn. We did something different. We said, identify the keywords relevant to the particular process. And when it did that, we converted that into what is known as a knowledge graph, which is saying, now that you've identified the keywords, use the surrounding text that lines up the sentence to understand how the process itself lines up. To the point solely from text, it was able to infer that if I was to have a crude oil, I would do this and that to it in order to get the output that my text is actually telling me. And when you extend that to the whole passage itself, it becomes more and more complex and intricate, learning new scenarios and new knowledge structure, to the point that if you were to isolate text, which is information, from action, which are the connectors, it's automatically knowing how the actual insight connects to action, so that when I ask it a particular query to do something, it knows exactly how to achieve it. And the beauty is, when we keep extending it to manuals, documents, this continues to grow to the point that it learned its own data and knowledge domain for petrochemical and refining. And every usage, every query that goes in, every feedback received improves that knowledge base, improves the language model to be better grounded to the understanding of petrochemical and refining. And the beauty is this can be extended to any other of those verticals within whether oil and gas or energy, because they all have same manuals, same operating procedures, same logs. The knowledge is there. It's just a case of how do we actually utilize and embed it. And that's what we unlocked. But now the second phase was, when we generate an answer, we can't get it wrong. Now, typically, what you would have in software is procedural code. Essentially, you would write a set of code that basically is a tick box action. Does it meet this criteria? Tick. Does it meet that criteria? Tick. Does it meet this criteria? Tick. And when you have about 80 or 90% coverage, which is a threshold determined based on your users, you'd say, okay, fine, this is verified. We can't have that. Not in this case, because it's not an option. So one of the biggest difficulties we had is how do we verify each output and make sure that it's correct and doesn't hallucinate? So one of my engineers had a really good idea. And he's sitting right there. And it was, what if we just build a model whose sole purpose is to do that? And I was like, that's intriguing. How are we going to get the data? And he said, give me 2 months. It took 2 weeks, which was awesome. Essentially, that's what the verifier model's purpose is. The verifier's job is to say, when a final answer is coming out from all of those models, should I send it to the main app, which is the Orbital LLM, or do I send it back to the rerouter so that the entire process can happen all over again? Right? And that cycle does happen. So You'll see that there's a loading time when a response is generated from Orbital. That's because it's a verifier essentially going through every response and saying, I'm not cool with this yet. It's missing this information. There's a better way of actually outputting this. I'm not cool with this. Do it again. And when that cycle is complete and the verifier gives a green light, only then the output is generated. And the verifier was trained with collecting countless amount of APC engineer feedback, as well as from the very same documentation, getting the factual accuracy correct, which means if I was to generate a reasoning, it has to match that and be found and cited from the documents itself. If not, then it's not going to be catered for. And finally, completeness, which is the fact that if we merge this with the physics understanding we have done to train the model, as well as getting the retrieval correct from the manuals, etc., as well as the feedback being checked, which is the structure of the output, only then the verifier says, yeah, it's ready to go. And these were the three categories used to train the verifier. And just like before with the retrieval model, every usage improves performance. And typically, when a query goes into the Orbital application, on average, you would run 2 loops for every query. And we keep optimizing it every time to try and bring it down to less, so that every time verifier and all the models are already in tune with what the verifier requires. At some point, the verifier would essentially become redundant once the model has baked all of that relevant knowledge. But less than 4 seconds is what this entire process runs for verification. So when we put the same query after giving the same exact information in other language models, we get answers like this, right? So this went through GPT, and GPT did this classic trick, which is sounding smart. But if you look at the actual highlighted parts, it's actually very vague. It's not direct in its output. It's generic but plausible. And it's still there, right?
Mm-hmm.
All right. It's just blacked out on my end. Oh, it's back. Okay. Sorry, I also just realized that the background is black, so there's actually something being presented there. But one of the key things that you'll realize with GPT is that it's true in some contexts when it's generic, but it's unrelated to the most of the real calls here. And that's the issue with other models and getting the right response. When you ask the same question to Orbital, you'll see that it actually is very chemically specific, naming the exact solvent that takes place, naming the exact operation that's taking place, so endothermic, so it knows exactly which direction it's actually happening. And it's grounded in the very behavior of that particular plant. And that is because of the retrieval model and the verifier working in tandem with the information being received from the time series in physics. Well, in this case, it's mostly verifier because of the generic question I asked. But that essentially is, as a whole, how Orbital works when a query goes in. All of that design and computation is what takes place for every query. But let's actually look at it in the real world, in the actual cases that we're piloting with. Now, this is a particular refinery on Earth. I'm not allowed to say what it is, and I won't, but if it slips out, you have to forget. Please. But either way, we're going to show you something awesome. So take a good look at this picture. Right. That thick black crust, or in this case a little bit brown here, but that thick black crust is known as coke buildup. It forms when the actual contents within these pipes, i.e. hydrocarbons, don't fully combust. It's like cholesterol in arteries. It really chokes the flow, right? And once it starts, the heat transfer fails, pressure drops, equipment strain, but the worst of all is the entire unit has to be shut down to clean this out. Can you imagine shutting down unit for multiple days and then somehow finding exactly where in this pipe wreckage the coke buildup is and then cleaning it out? Because that's how it's actually happened today. And the kicker is we don't know when or how it occurs over time. We only react to it when it has occurred, which is already too late. So when I rocked up at this refinery office, and I was wearing a Metallica Master of Puppets t-shirt and really thick black jeans on a 40-degree day, so it wasn't the best choice of clothing, with my backpack, and I rolled up with a force of 14 people in front of me, and I told them, which is exactly what I'm going to tell you now, is what if your refinery data could tell you exactly when this will happen and explain how and why? They all laughed, except for one. The one person was the VP of refining there, and he just stared at me and was the one that gave us our opportunity to trial it here. And upon training Orbital on this problem case and identifying exactly what had happened and why, we handed a report to them in about, I think it was 6.5 or 8 weeks. And their engineers came back and said, had we implemented the actual changes you would have said, that would have saved us 8 days of downtime. Now, this unit makes $710,000 a day when it runs clean. So by identifying exactly which sensors were having an impact, we identified exactly which equipment was having that coke buildup, which didn't track with the physics. And because of that, we would have actually been able to give them a recommendation on how to avert it. And that recommendation, if implemented, they evaluated, it came back, would have been 8 days of downtime that could have been eliminated and prevented by their team. Now, the cool thing is Orbital achieved an insane amount of accuracy when in steady state, an error of only 0.15%. Right? I believe airline tolerances aren't like that with autopilot. But this isn't the cool part, right? This is awesome. But the cool part is the fact that in their data, there were few sensors that malfunctioned, as in they were anomalous. They weren't reporting the right results, which is very typical in refinery, where sensors, to some degree, lie because their numbers also shift. And what had happened was their models during this anomalous sensor wasn't able to predict coke buildup. In that case, they actually just bottom lined at 0 because it wasn't trained for that distribution. So as soon as sensor results were out of the norm, the model fails, right? Which is expected because it's out of the normal distribution. This is typically known as drift. Now, the beauty is, because Orbital reasons every prediction with physics, it essentially knows if something is burning and there's no oxygen coming in, then there's something wrong with the oxygen transmitter here. So let's reroute my understanding of physics and information coming from other sensors and inform my prediction according to that. You can only do that once you're grounded by physics. And because of that, even when the sensors were giving anomalous results, Orbital maintained its prediction close to the ground truth. Can you see that red line? You all can, right? That's the Orbital prediction. And that really blew everyone's mind, including my own, because we were like, we inherently knew that this would be possible with physics, but to see it on the actual results metrically, and because it understood the physics, it was also able to pinpoint exactly the value and the issue with the plant that led to the coke buildup. To the point when we just handed the reasoning to them, that's where they came back with the fact 8 days could have been prevented, right? And the beauty is, this is just one unit, right? There's hundreds of units like this, and each one is tied to an economic value. Here's another one. So there was a refinery in Europe where we went to, and in particular, what they wanted to experiment with is predict and optimize what is known as energy intensity index. So refineries run on 2 things, crude oil and energy. And energy isn't cheap, nor is it free, right? It's a cost, it's carbon, it's load on the grid, it's your footprint. And energy intensity index is a way to measure that burden on the refinery itself. Think of it like refineries miles per gallon, right? So higher the miles per gallon, the more efficient the car, because you get more out of it. Just like that, refinery energy intensity index. Lower the energy intensity index, the less the burden of energy on refinery to get the same product, the more efficient it runs. And every 1 point decrease in energy intensity index is a $2 million a year win. That's a check they get to keep because of the amount of astronomical cost for running energy in a refinery. So I asked a similar question to them too, which is, what if you could just ask, why is our energy intensity index rising today? And in this particular case, Orbital found a 2-point decrease in energy intensity index. Found variables that could result in reducing energy intensity index by 2 points when they had a spike that year. $4 million, right? $2 million per point of new beta that they could get on that front. So the way it did it, the way Orbital achieved it, was we had the energy intensity index ground truth that they had collected from consultants over a period of months and years. And it was something like this. And there was one particular point where it spiked really high. Now, Orbital, given just sensor data from equipment, was trained to first be able to predict that exact value, because then it learns the correlation of the equipment, how it runs, to the energy intensity index. And it achieved 98% accuracy. None of their models ever reached it. And because it learned that correlation deep within the embedding matrix of the model to estimate how sensor data from equipments relate to the energy intensity index, we were able to create essentially a plot where we essentially showed what were the biggest influencing factors to the energy intensity index directly tagged to the actual equipment itself. And just by targeting the right equipment in order, which was a top 20 in this case, they were able to identify exactly why the energy spiked and what part of their plant was running inefficiently, to be able to maximize high octane yield, reduce fuel gas, and reduce steam makeup. Same playbook, any unit. Similar, it goes back to the idea of if we're able to understand all the data and optimize, we can add that 50 cents to that share, that margin, right? And that's where you unlock new throughput and also new efficiency gains. So just like this, there are hundreds more units, and each tied to an economic value. And the beauty is that energy and other values within the refineries that need to be optimized are all largely controllable costs if well understood. So before I hand it over to Cal for closing thoughts, a few things I want you to take away from this exact presentation before I become a barrier to drinks is the fact that Orbital is all of the research algorithms we just discussed out of the lab and deployed in the real world as a product to drive economic impact. It's real science for real value. Every refinery leaks a lot of money and also throws throughput on the table. And a small addition can move that number fast. And the foundation of it is to make AI explainable and trustworthy whilst making it high precision for the real world environments. Thank you very much for listening.